Greetings, fellow physics teachers. Welcome to another interesting episode of Physics in Everyday Life. In our last encounter, we looked into the power and efficiency of machines, remember? We said that machines do work and that the rate of doing work is what we call power. On the other hand, efficiency was defined as the ratio of work output to the work input multiplied by 100%. This can also be explained as the ratio of the useful energy output and energy input multiplied by 100%. And because of energy transformation, the efficiency of machines is always less than 100%. Today, we're going to discuss another machine, but this time it's none other than our body, the human machine. We have learned that a complex machine is made up of several simple machines. Do you know what types of machines are found in the human body? That's one of our points for discussion today. Also, we will find out how powerful and efficient the human body can be as it performs work. So, join us today as we encounter and uncover the secrets of the human machine. And let's go Physics Scout! Before we start examining the human body, let us recall what we have learned about simple machines. We learned that there are two general types of simple machines, levers and inclined planes. Can you tell the difference between these two types of machines? Now, this is a pair of pliers. One of its uses is for pulling out small nails. As you can see, pliers have this pivoting portion or turning part, and this is called a fulcrum. The fulcrum is a part peculiar to levers, so we can say that this gadget, the pliers, is a lever. Now let us look at this one. This is a slanting board. We can use this board when we want to transfer heavy objects from a lower place to a higher one or vice versa. For instance, instead of lifting this box from this position to a higher position, we can use the inclined plane. We can slide it up the inclined plane like this, or slide it down like this. This slanting board is a good example of an inclined plane. Okay, now, can you tell me what types of simple machines are found in this pair of scissors? Since it has a fulcrum here, it can be considered as a lever. But this sharp edge here is a variation of an inclined plane, and we call this sharp edge a wedge. So this pair of scissors is a combination of a lever and an inclined plane. This pulley and this bicycle are both classified as levers. Screws, knives, and other cutting tools are variations of the inclined plane. The inventions of machines made everyday life more comfortable by making ordinary activities easier to perform. Machines make it possible to travel faster to distant places or even to outer space. They also help us in doing our household chores like cooking, ironing, or doing the laundry. In the workplace, machines help us save time and energy in many countless ways. Now, as we mentioned earlier, the human body is also a machine. And I left you with the question, what simple machines are found in the human body? This when we return. Fellow teachers, welcome back to our program, Physics in Everyday Life. As promised, we will now show you the human body as a machine. And with us here is our fitness-conscious friend, Robert. Hi, Robert.
Hi, Dr. Domingo. Would you like to join me with my workout?
Well, actually, I'm all dressed up for it, but maybe some other time. I am doing already my own kind of work. All right, Robert, will you be kind enough to demonstrate to us some crunches using your dumbbell here?
Sure, no problem.
You see, the exercise here is for strengthening arm muscles. Watch carefully the movement of his lower arms. What type of simple machine is the body's lower arm? The lower arm is a lever, where the input force is somewhere here, between the output force equal to the weight of this dumbbell here, and the fulcrum, which is the pivot here. So we can say that our lower arm is a third-class lever. We will now show you an actual schematic diagram of the forces involved in the lower arm in the dumbbell exercise. We have here our diagram, and we can see here that the input force is in this position. The output force is here, which is equal to the weight of the dumbbell, and the fulcrum is at this point. The lower arm is supported at the elbow, which corresponds to the fulcrum. All right, let's look at this other diagram here. When an object is lifted, this muscle called the biceps contracts or tightens, bends the elbow, and exerts an input force greater than the output force to raise the arm. The output force is equal to the weight of the object being lifted. Let's take note of the models found on the right-hand side here. These diagrams show us that as the arm is raised to lift the object, then the input force, F sub I, increases. The contractions of the biceps also become greater if the object lifted becomes heavier. In this case, the input force must also be greater. All right, now, let's go to this last diagram here. Our feet, when we walk or run or climb stairs, are also levers. Let's look at the diagram here. In this case, the output force, F sub O, is between the fulcrum and the input force, F sub I. The foot is then a second-class lever where the fulcrum lies along the joints of the toes and the soles. In this type of lever, the input force is less than the output force, and the output force is equal to the weight of the human body.